Okay, let's discuss inverse trig functions. An inverse function is a function that will kind of reverse the concept. So typically, when we're doing, let's say, a sine function, we input the angle, and what comes out is the ratio, right? So here, the sine of pi over 6 is equal to 1/2, right? An inverse function reverses that, or rather, it maps it back. So an inverse sine, and I'll show you the notation for all of them in a second, but the inverse sine looks like a -1 power, does not mean -1 power as in the notation you're used to seeing on numbers. If it's on function notation, it means inverse function, not fraction stuff, okay? But the inverse maps back. So the inverse will say, oh, I have the ratio of 1/2. What angle produced that ratio? And it will map it back to pi over 6. Okay, so the inverse takes the ratio and figures out what angle we're talking about. Okay, so let's talk about how you did inverses before we looked at trigonometry. So previous math class, you found the inverse function by doing a series of steps, right? We switched the x's and y's, you solved for your new y, you renamed it with that -1 exponent. That means inverse function, not fraction, okay? So we're going to be doing that eventually. At first, though, we're just going to talk about when we can have an inverse versus when we can't have an inverse. Okay, so just to follow my notes here, regular trig functions, in goes an angle, out goes a ratio. Inverse trig functions, in goes the ratio, out comes the angle like we just saw. Okay, notationally, sine, in would go an angle, out would come a ratio. An inverse, in will go a ratio, out will come the angle. Okay, very similarly for cosine and tangent and the reciprocals, I'll just lay out a couple of them here. Cosine, in with an angle, out with a ratio. Inverse, cosine, oops, I don't mean that. In with a ratio, out with an angle. Tangent, regular tangent function, in with an angle, out with a ratio of the y over x. The inverse tangent, in with a ratio, out with an angle. Now, I've been saying the word inverse tangent, inverse cosine, inverse sine. Some textbooks don't like using that notation. Some textbooks would rather say arc tangent. Do they mean inverse? Absolutely. But they say arc tangent, arc sine, arc cosine instead. I'm going to try to use both terminology um, at random times, just so you're familiar with both. Okay, now, if you recall from previous math classes, when you've had inverse functions, they had to be one-to-one functions. What we mean by that is that each angle can only have one ratio, and each ratio can only have one angle. We are presented with a problem when it comes to the trig functions, though, with that. Here is why. Let's look at this unit circle. If we focus on just the sine values, +1/2, +√2/2, +√3, +1, +√3/3. I already had that here. So when I do arc sine of root 3 over 2, I have to answer pi over 3, not 2 pi over 3. It has to map back to only one angle. So that means for for sine, none of these angles can be used. None of these angles can be used as what we would get for an answer. So in other words, the range. None of these. Because here, the y value is 0, and same here, so we can't have it. Here, the y value is -1/2. Same here. One of them has to go. Same here, here, and here, right? So this one would be okay. So what we're saying is when it comes to the sine value, we only allow angles from -pi over 2 up to +pi over 2. Okay? The ratios, -1 to 0 to +1. Okay? So I'm going to come over here. I'm going to erase this in a minute because I just made a scribbly mess out of it. But when it comes to the sine values, we just established, we just established that we are allowed to go from -pi over 2 to +pi over 2. Okay, for angles. The ratios go from -1 to +1. Okay, so let's write that. For the inverse sine, the ratio goes from -1 to 1, and the angle goes from -pi over 2 to +pi over 2. Okay. Now let's look at cosine. When looking at our unit circle, we're going to look at all the x values because those are the cosines. X values are positives here, 0 here, negative here. Now, this negative x value and this negative x value are the same. I can't have a ratio map back to an angle that happens more than once. So I'm only allowed to map it back to one of these angles, not both. So I get rid of all of them. If you have a negative ratio, you're going to map back to an angle here in quadrant 2. If you have a positive ratio, a positive root 3 over 2, again, you can't have it map back to do different angles. That's not 1-to-1. It has to only map back to 1. So we're just going to get rid of those. So we will allow or restrict, we call this restricting the domain and restricting the range. Well, the range is generally restricted, but we're going to restrict the domain for cosine to go from 0 to 180 degrees. And the ratio goes from 1 to -1, or vice versa, really. Okay. So in order to do an inverse, the ratios are from -1 to 1. The angles are from 0 to pi. So for cosine, these are gone. For cosine, if you have a positive ratio, it'll return an angle in quadrant 1. If you have a negative ratio, it'll return an angle in quadrant 2. So you get to go from 0 to 180 degrees, or pi. Okay? All right. So cosine, inverse cosine, ratio equals angle. The ratio between -1 and 1. The angle between 0 and pi. And it can equal 0 or pi. All right. Tangent. Okay. 1 to 1 means 1 ratio per angle, 1 angle per ratio, right? So when we look at the tangent values, now this is going to be the y over the axis. When we do tangents, we get positive ratios in quadrant 1 because they're both positive. We will get negative ratios in quadrant 2. When we're looking at 90 degrees, if you think about what the graph of tangent looked like, it was undefined, the tangent of 90 degrees, okay? The tangent of an angle in quadrant 3 is positive. That would be a positive ratio. And quadrant 4 would be a negative ratio. And again, this is undefined. So I have to be able to map back to 1 and only 1. So when we have a positive ratio, we're going to allow it to map back to quadrant 1 only. Okay. Now, I don't know at what point, but at some point it was decided that we would have our negative ratios to be 1 to 1 map back to the quadrant 4 angles. So negative, our angles, is negative pi over 2 to positive pi over 2. Okay. So when it comes to tangent, the inverse tangent, the ratio, now if you think about the graph of the tangent function, or you think about these ratios, right? As we get closer to, let's see, let's do close to pi over 2. The y value is close to 1. The x value is close to 0. So that will in turn, the ratio of that, right, y over x will go to infinity, positive infinity. So this ratio is actually all real numbers, or negative infinity to infinity, okay? The angle that we're allowing is negative pi over 2 to pi over 2. Now, I don't have an or equal to sign there. And the reason I don't have an or equal to sign is because at pi over 2, the tangent is an asymptote. And at negative pi over 2, the tangent is an asymptote. So those actual angles don't have a corresponding ratio, okay? So if we restrict it to go from negative pi over 2 to positive pi over 2, we can have a inverse for the tangent function, okay? Now, it's interesting to note that for sine and for tangent, they have the same restrictions, okay? Now let's look at their reciprocals, okay? So cosecant's going to be very similar. So inverse cosecant, ratio, outcomes in angle. And that's actually going to operate the same way as the sine with the restrictions. So with one exception. Remember when we graphed the cosecant function, how it looked like a u up, a u down, a u up, a u down. Okay. To be one-to-one, let's go back to your algebra class again. It has to pass a horizontal and a vertical line test, right? So we actually cut this off and this off, which means we go to negative pi over 2 to positive pi over 2 to keep it one-to-one. Okay. And then let's talk ratios. Well, if the ratios for sine went from -1 to 1, the ratios for cosecant is anything greater than 1 or anything less than -1. And I should add an or equal to. Okay. So we say the ratio is less than or equal to -1 or greater than or equal to 1. The theta is going to be between or equal to negative pi over 2 up to positive pi over 2. Ooh, I have to be careful here. Positive pi over 2. What happens right here? At 0. There's an asymptote, right? Can't be 0. Yep. All right. Let's see. I wonder if, for the sake, well, secant, reciprocal of cosine, we actually exclude the same way. And then we go from 0 to pi, except for what happens at pi over 2. It's undefined. So for an inverse secant, theta, I can run it the same way I did it for cosecant, like with doing in inequalities, but I could just notationally doing it a little bit different. See if this makes sense to you. I can go from 0 to pi over 2, but don't include pi over 2. And then from pi over 2, don't include it, to pi. So it's just a different way to write like intervals when you want to exclude one spot. All right, let's talk about ratios. The ratios are less than or equal to -1, or the ratios is greater than or equal to +1. Okay. Cotangent is interesting because cotangent has the undefines at 0 and at pi. Think about our graph of the other trig functions. Okay. So we actually, if we can avoid an asymptote, we will. We couldn't for the previous two problems, or previous two, but we're going to slice cotangent slightly different so it can have a one-to-oneness. We're going to slice it from 0 to pi. So that means when we have a cotangent inverse, theta is going to go from 0 to pi. And notice I'm not including them because they were asymptotes on the graph, right? And then let's talk about the ratio. The ratio, and if you think about what the graph of cotangent looked like, the ratios were all real numbers. So -infinity to infinity. Okay. Now, some instructors teach the one-to-oneness by sketching the graphs, right? So when we sketch the graph of cotangent, it looks like that for one period. So to hit one period, we're 0 to pi. So we don't allow a repeat because then you would have, you would lose your one-to-oneness. Okay, so for tangent, there's one period and we don't have to jump over an asymptote. Don't do a duplicate or don't do the next period because you lose your one-to-oneness. Now, sine and cosine, the sine function looks like so to keep our one-to-oneness, we have to slice here to here. Can't include any of that or any of that because then you have duplicate x's for each y, right? So we would slice it and go from negative pi over 2 to positive pi over 2. Okay. For cosine, very similarly, we would slice it here at 0 and here at pi, 0 to pi. So it has one-to-oneness, 1x for each y, 1y for each x. Cosecant, if you had a graph of cosecant, it would look like, let's see, this cosecant is a u here, a u here, right? So to have it be one-to-one, we're going to go here to here. Get rid of all of this, get rid of all of this, and everything else after that. So negative pi over 2 to positive pi over 2. For secant, the graph of secant, u here, u here, u here. We are going to slice it here and get rid of all this, and slice it here at pi and get rid of all this. Now there's 1x for each y. All right. I know it's a lot. That is why let's take a break. In the next video, we'll jump into examples. Now we just talked about domain and range for inverses. Okay. Jump into examples next.